There we go. We have finished off the magnetism unit. So what are some types of written questions that I'm going to ask? Well, certainly make sure you look at the ultimate review. If you work your way through that, very little I throw at you, if any, on the test is going to be a real surprise. There is one medium curveball multiple choice, but I would say about 75% of my kids get that one still, I hope. Number one, a stream of protons is acted upon by a magnetic force of that while traveling perpendicular. What if it was traveling parallel to a magnetic field? What would the net force be? It's a trick question. 0. It's when a charge cuts across magnetic field lines, and the explanation is complicated. I'm not going to get into it, but it's got to be going perpendicular. Or I said you could find the perpendicular component, and Sammy, we looked at that a bit, but I said, meh, we're going to just go with what we got, okay? What speed? Okay. The force, the magnetic force on a moving charge is QVB, as long as the V's and the B's are perpendicular to each other. Hello, my friend. You're going to come see me after school today, or we'll talk later. I want to get the V by itself, which is going to be F over QB. Let's see. 5.8 times 10 to the negative 14 all over Q. It's a proton. 1.6 times 10 to the negative 19. B, 0.6. 5.8 times 10 to the negative 14 divided by bracket 1.6 times 10 to the negative 19 times 0.6. Do y'all get 6.04 times 10 to the 1, 2, 3, 4, 5? Yeah? And as I said before, for each of these, 1, 2, 3 variables, any 3, you should be able to find the fourth. Okay. Hey, now let's apply that. Oh, no, sorry, now we got a wire. Now we have the force on a wire. Now remember the force on a wire a little bit differently. It says if a wire carrying a current of 5.2 amps, as shown in the above diagram, if the force that the wire experiences that, what's the strength of the magnetic field? So we said the force on a wire is Bill, so I guess they want the magnetic field, which is going to be the force divided by IL, which is going to be 0.024, that is 2.4 times 10 to negative 2, divided by 5.2. And then here's the question. I got 2 lengths in this question. I wonder which length I use. Would I use the total length of the wire, or would I use the length of the wire that's inside the magnetic field? Would I use this one, or would I use this one? What would make more sense in terms of physics? Which section do you think is undergoing the force? The field. You're going to find when you do the review, if you haven't already, and you're going to find on the test, they almost always give you both lengths, because on multiple choice, it gives them one more wrong answer that might show up that they can include, that you can do the math. There's my answer. No, you're wrong. So you'll find they always give you both. So if you use the 8 centimeters, you're going to get 1.5 out of 2, but it's going to be the 4.2 centimeters. And of course, you have to do a conversion. So this is a magnetic field strength of 0.024 divided by 5.2 times 0.042, 0.11 Teslas. 1.1 times 10 to negative 1 Teslas, but yeah. Okay. Otherwise, I would probably go, 1 mark for that, half mark for the numbers, half mark for the answers, or something like that. 0.11 Teslas, fairly big. Fairly big. What's the direction of the magnetic force? So let's see. Current going that way. Which way is the magnetic field? Into the page. Which way will this wire feel a force? Okay, down the page, which I hope is one of your answers. Down the page, 1 mark. Now, Kelly, on your test, I would have also no problem making you do some of this backwards. In other words, instead of saying find the force, I could tell you what direction the force was, tell you what direction the magnetic field was, and say, hey, which way is the current going? Or I could tell you what direction, Manisha, the force is, tell you which way the current is, and say which way is the magnetic, which way do your fingers have to point? Okay, so all three of those are fair game. That's the complicated right-hand rule. We learned 3 right-hand rules. That's the right-hand motor rule. Now, the good news is we're going to be flogging that again in today's lesson and the next lesson, in fact, the next couple lessons, because this third rule explains an awful lot about how we generate power and how electric motors work, and therefore how electric generators work. Next page. Electron, okay. You know what? It's going to be QVB. It wants the magnetic force. Piece of cake. Q, it's an electron. V, it is moving perpendicularly. I double-checked. 6.2 times 10 to the 6th. Magnetic field, 8.5 times 10 to the negative 3. Uh, 8.43 times 10 to the negative 15, is that right? 8.43 times 8.43 times 10 to the negative 15 newtons. 1 mark for that, 1 mark for that. If you got the right answer, 2 out of 2. The electron is forced into a circle. Oh, did they say circle? That must mean that magnetic force equals centripetal force. That must mean that QVB equals mv squared over r. What do they want me to get by itself? The r. By the way, just nerd moment. What do I have on the top? Once I cross out this squared, what do I have on the top? mv. Hey, what is mass times velocity? Yeah, it turns out that's actually the momentum. If I got mv by itself, I'd have the momentum. Or they could give me the momentum instead of the actual mass and velocity. It would terrify me at first because you'd be going, wait a minute. No. Let's see here. Get the r. Now, the r is on the bottom, so I'm going to move the r to the top and move the qv to the bottom. I think I'm going to get this. R equals mv over qb. It's going to be m. It's an electron. 9.11 times 10 to the negative 31. V, please tell me there was a speed. 6.2 times 10 to the 6th. Q, it's an electron. B, what was the magnetic field? 0.0085, or 8.5 times 10 to the negative 3. 9.11. 6.2. The decimal didn't show up there. Let's do that. Times 10 to the 6th divided by bracket 1.6, negative 19. 4.1 times 10 to the negative 4.2, 4.15 times 10 to the negative 3. Is that right? That's small. I got to change these numbers, but okay. Well, if Jordan got it, then we're 4.15 times 10 to the negative 3 units. Radius. Oh, meters. Got to be. Okay. Last question says, hey, what's its kinetic energy? Oh, I just threw that in. Kinetic energy is going to be a half mv squared. It's going to be 0.5, 9.11 times 10 to the negative 31. 6.2 times 10 to the 6th. Hey, wait a minute. Would it be possible for me to give you the kinetic energy and have you actually cleverly plug it into there and work your way backwards? I'm trying to think of curveballs that I can throw at you on your test, especially in the multiple choice section. Hey, yeah, if they gave me the kinetic energy, I could probably find the velocity and the whatever I needed to work with Hard joke. Knock, knock. Squared! Right? You were just bursting, right? Absolutely. Almost forgot, Mr. Dueck. Do we get 1.75 times 10 to the negative 17th joules? Not very much. Ke equals 1.75 times 10 to the negative 17th joules. 1 mark for the first line, 1 mark for the second line. Again, if you got the right answer, full marks. Oh, one more question. Good. I was going, wait a minute, didn't I throw any solenoid stuff on here? What magnetic field strength inside a solenoid of length 3.2 meters having 600 turns of wire? What is the, oh, well, the magnetic field from a solenoid is going to be mu naught N times I over L. That's if they give me the total number of turns of wire, which they did, and the total length, which they did. Remember, they can also sometimes give you the, and where this is turns per meter, or coils per meter, or windings per meter, or whatever synonym, loops per meter, whatever synonym you can come up with per meter. This is going to be mu naught. Oh, the permeability of free space. 600, 4.5, 0.032, 4 pi. Again, some of you with cheaper calculators have to go pi 4. Or pi times 4. You'll get 0.106 Teslas. Half mark, 1 mark, 1 mark. Can you give yourself a lovely score out of 13, please? Lesson 1, by the way, this is really one big unit, all called magnetism, but I've broken it up into 2 parts. Electromagnetic forces, and then this next unit is electromagnetic induction. Again, a reminder, you guys can write your tests during your study blocks. Read along with me. It says this, in the previous unit, we learned that when electric charges move, they produce a magnetic field in a wire, the whole right-hand rule stuff. In addition, a magnetic field will exert a force on moving charges. Early in the 19th century, scientists such as Michael Faraday, one of my heroes, and Joseph Henry were aware of these properties, and both of them said this. Look. You guys with me? I need you focused here. If current can create magnetism, can't a magnetic field create current? What they were trying to find was a way to generate power. Up until then, all electricity came from chemical reaction batteries. What they were trying to say, Elijah, is maybe there is some mechanical way that we can create electricity, electrical energy. Recall that electromotive force, or EMF, symbol curly E, it's an archaic word that refers not to a force but to the voltage of a cell. We still use that symbol in these questions in honor of Faraday and Henry. We're going to be using the term EMF. They thought it was a force. They didn't realize it's not. It's a voltage, like a height in a ski hill. So voltage and EMF, for our intents and purposes, mean the same thing. That's technically not quite true, but it will be true for Physics 12 and can be used interchangeably. This is measured in volts. If a piece of wire moves through a magnetic field, all of the electrons, oh, sorry, we're not looking at electrons. We're going to look at protons, even though the protons don't move. We're going to pretend that they do. All of the charges in a wire will experience magnetic forces. The negatives will be moved to one end, and that'll leave the other end positive. We can use the right-hand rule to determine the end. So Example 1 says, which end of this wire will be negatively charged? This is a region into the page. So if you want to, you can put X's there. That's what those little lines are supposed to mean. So what we have here, Kelly, is a piece of wire. Hey, how about a metal bar? And we're moving it downwards through a magnetic field into the page. And what I'd like we're going to focus on is one charge. Let's, Nathan, put a positive charge dead center right there. Now, this bar is filled with trillions of positive and negative charges, but that's okay. We're going to look at one. That charge is stuck inside this metal bar, this wire. Which way is this charge moving down the page? So point your thumbs down the page. Which way is the magnetic field? So extend your fingers like you're high-fiving into the... So Ashley, it's going to be down the page, into the page. So on your desk, if you put it flat, it's going to be pointing the thumb towards yourself, extending your fingers into your desk, right, whichever way. Which way will the positives get pushed? To the left, to the right, or nowhere? This is going to become positive. Which side will become negative then? This side will become negative. And what you've just done is you've separated charges. No? Down, magnetic field into the page. You're using your left hand? Really? I'm a lefty too. You have an advantage. You can hold the pen in your left and do the right hand rule. Everyone else, you hear me always put the pen down. You don't have to. Cliff, L for left, R for right. Just don't do that. Okay. What you've done is you've separated charges. And to separate charges, you guys good? Okay, I need you focused here. That takes work. And that means we have voltage, because voltage is defined as essentially, if you were to move this wire down the page in a magnetic field pointing into the page, you have done the same thing that the chairlift analogy in our circuit battery does. You have separated charges. You have given positive charges more height, more voltage. But we call this voltage induced voltage by motion, motion voltage, because the energy in this case comes not from chemistry, but from motion. You with me so far? We've separated charges. One side of this wire will be positively charged. One side of this wire will be negatively charged. In other words, a motion can induce an EMF, and remember, EMF is the same as voltage. Example 2 says, hey, let's see if we can find an expression for how much voltage that we can induce. We defined voltage as potential energy per coulomb. Or you can think of that as work per charge. How much work has been done on each charge? How much energy each charge has absorbed? What's the definition of work? Way back when, this is good review, from Physics 11, work equals what times what? It's on your formula sheet too. You're right, someone started to say it. Force times distance. So this is force times distance per coulomb. I'm going to erase the times. FD over Q. But which force? I would argue magnetic force, FB. Make sure the B is a subscript. I'm not saying times, right? That's the force. Okay. Wasn't the magnetic force QVB times distance over Q? Oh, I see something, Sammy. What do you see right now already? turns out, okay, so here is our first equation. Voltage, or on your formula sheet, it's EMF, that's equal to B, except instead of distance, because we're talking about the length of a wire, what variable have we used in this unit for length of something? LV. As long as the magnetic field and the length and the velocity are all at right angles to each other. You want to know how many volts you're causing, how many volts you're inducing? Multiply the magnetic field times the length of the bar or the wire times how fast you're moving it. You want more voltage? Move it faster. You want less voltage? Don't move it so fast. You want more voltage? Increase your magnetic field. Oh, you want more voltage? Longer wire in the magnetic field. Okay? So, where B is the external magnetic field in Teslas, L is the length of wire, V is the speed of the wire, and they're perpendicular. You only get volts when all of them are at right angles to each other. We're going to talk about that as well. If they're not perpendicular, you only get a small amount of voltage. Look at example 3. Next page. Do you see the difference here? Instead of having the wire crosswise this way to the velocity, we have the wire parallel to the velocity. Again, let's look at that one positive charge sitting in the middle right there. Which way is that one positive charge sitting in the middle? Moving down the page. So all of you point your thumb down the page. Which way is the magnetic field? Your right thumb. Which way is the magnetic field? Into the page. Sammy, which way will that positive charge feel a force? To the? Now here's the problem. Can it move very far to the right if the wire is oriented vertically and it's a thin wire? Can that positive charge move very far to the right? Can the negative charges move very far to the left? Can you really separate the charge? I mean, technically you are. Barely. You're technically going to get a voltage, but not much of one. Okay? So, positives would move that way. Negatives would move that way, but we would say something like this. There is no distance to separate the positive and negative charges. Compare that. So the wire this way, Claire, they'll separate. They just got nowhere to go. They're not really going to be very separated from each other. Yay, you move them apart a little, especially if it's a thin wire. Here, in this, where are we? In this picture, hey, you can really separate them. You can get a whole bunch of positives on one end, a whole bunch of negatives on the other end. Yaha! Here. Meh. So a classic multiple choice question in this unit is they'll give you a picture of 4 different situations, and they'll say which one will induce the biggest voltage, and I guarantee a couple of the bars will be moving parallel to the magnetic field or parallel to the direction of motion. Example 4. Find the voltage induced by motion across the ends of the moving wire and indicate the polarity. So we have to decipher this. The bar, that's the wire. What direction is the magnetic field? Look at the picture. Down the page. Which direction is the velocity? What have I tried to show with this diagram? Okay, into the page. So, okay, let's get the direction. So we have velocity into the page. You're going to point your thumb into the page. Magnetic field down the page. Which way will positives be forced? Now, this is a little, okay, stop. If you need to spin your paper 90 degrees, or, hey, let's use this into the page, magnetic field down the page. Which way will the positives be forced? To the left. Which way will the negatives be forced? To the? So, this end is going to become positive. This end is going to become negative. How many volts? Because that's the first thing. It asked, find the voltage. So the induced voltage is equal to BLV. It's equal to 1.25 Teslas. 0.8, 5.25 meters per second. 1.25 times 0.8 times 5.25. I'm missing a times there. 1.25 times 0.8 times 5.25. Oh, nearly a 6-volt battery. Close. 5.25 volts. Is that right? Double check me.
Yeah.
By the way, this is terribly inefficient, but we start here and we're going to find a much more efficient way to generate the voltage. You spin it, but we're going to get there. Okay? Back in the 1950s and the 1960s and the 1970s, and thankfully it ended in the 80s, on airplanes, most flights were smoking flights because most people smoked. I did one time a Greyhound bus trip from Regina, Saskatchewan back to Vancouver. It's 2 days, and that was when the buses had a smoking section and a non-smoking section. The non-smoking section was the first 7 rows. The smoking section was everything behind row 7. I was in row 7. As someone who's not a smoker, it was not a pleasant experience. So anyways, hey, find the voltage induced, the motion voltage induced across the wings of an airplane. Let me see. Is an airplane sort of like a metal bar? Yeah. Is it traveling through a magnetic field? Earth's? You'll induce a voltage. How big? Let's see. Let's assume that the Earth's magnetic field, is down into the page. Let's get the polarity first. So which way, here's our, let's put a little positive charge right there. Which way is this positive charge traveling? To the right, so point your thumbs to the right. Which way is the magnetic field? Into the page. Which way will the positive get forced? This wing will become positively charged. This wing will become negatively charged. You'll separate charges. Magnetic field, they said, is 0.008. Mr. Dueck, I thought you said the Earth's magnetic field was like 10 to the negative. This is up at altitude. The magnetic field up there is stronger than, anyways, for what it's worth. Which length am I going to use? The 60 or the 150? Why not the 150? That's in the same direction as the motion of voltage. Technically, you know what? You don't be separating charges here and here. You won't be. What you will be is you'll be separating charges across here. So I'm going to use the 60. Oh, V, 320. How many volts? Hey, 154? How many volts come out of a plug? 120. Alternating current from a plug. This would be direct current. But this was the reason I went on my little smoking rant. This is how they used to actually power the in-seat cigarette lighters. May as well use it. Okay. Now, that's not free energy. Your gas mileage is lower by exactly the same amount of work that you do in separating those charges. So it's not free energy, but may as well use it. Okay. Kind of cool. How could we use it? Well, what we're going to do is we're going to conduct this moving metal strip to conducting rails. So in my little picture here, these are metal wires that are bare, and we're going to slide this metal strip to the right while it's on top of those metal wires. Okay? Oh, and we'll put a resistor in there just because we don't want to short circuit. So we can get current flow. Example 6 says, show the polarity of the moving wire, show that the polarity of the moving wire is like a cell to the right. It's like a battery. Let's see. Here's my little positive charge. Let's draw him in right there. Which way is this little positive charge moving? To the? Point your thumbs to the right. Which way is the magnetic field? I have dots. What are those supposed to mean? Out of the page. So which way will the positive get forced? Okay, this is the same as having a battery that looks like this, except now the charges, although they get forced down, they have somewhere to go. They'll now jump to this wire, jump through here. They'll go through this resistor. And they'll end up back here. And holy smokes, you've got a circuit. You could light a light bulb, replace the resistor with a light bulb. As you slid this bar sideways, the light bulb would glow. The faster you slid it, the brighter the bulb. And here's what's weird. The faster you slid this bar, you would feel a force pulling against you. You would feel something invisible resisting you. It wouldn't just be straight friction. It wouldn't be the mass of the bar, because you're used to what those feel like. You would feel a force resisting you. So we're getting close to our current electric grid. We're saying, hey, just by sliding something, I can not only induce a voltage, if I attach wires on the end, now I can get a current going. Cool. Faraday and Henry were starting to think some good stuff here. If the current is moving through the metal strip, then there's a magnetic force on the wire that tends to slow it down, like I just said. Show you what I mean. As soon as you start pulling it, not only is this positive charge moving that way, what other direction is this positive charge moving? Because now it's a current, right? So, okay, draw the positive charge right here. Not only is it moving sideways, but because you've now got a continuous loop of current, it's moving down. Point your thumbs down the page. Magnetic field out of the page. Okay, I got to go kind of like that. Which way is your palm pointing? Left. I'm pulling this to the right. Which way will I feel a force? Acting to the left. That's what you felt, Callum. When you tried to crank, what the? That's that force. We're going to talk about the rotational one later, but that's that force. So, what we're really saying, by the way, Alex, is you can't get free energy. The more you use, the faster you pull this, the more voltage and therefore more current you want to try and create. The faster the charges are going to be moving through this circuit down the page, the bigger force you'll feel resisting you. Sorry. I could see you were thinking about your Nobel Prize perpetual motion machine. What if we put it on a hill and let gravity pull it? No. Sorry. Okay. So, let's put it all together. The magnetic strip, the metal strip below is 12 centimeters long. It's moving at 4.7 meters per second. The external magnetic field is 0.08. It's out of the page, Tesla's. And the resistance of the rail circuit is 0.025 ohms. Find A, the induced motion, B, the induced current, and C, the magnetic force on the strip. Okay. You ready? Induced voltage, that's voltage equals B times L times V. On your formula sheet, by the way, if you didn't notice. Here's our little positive charge. By the way, if the magnetic field was into the page, all that would happen is this circuit would reverse itself, and now the current would be flowing up through the bar. Is that what would happen if you started rotating it? That's why we have alternating current coming out of our plugs. It's much easier to create alternating current. Okay. Anyways, hey, what's the magnetic field, Curtis, in Tesla's? 0.08. Is that what I said? Yep. Length of the bar, 0.12. Speed, 4.7, which is not very fast, meters per second, right? How many volts will this generate? .08 times 0.12 times 4.7. You get 0.045 volts. Not much. But remember, EMF, that's the same as voltage. Okay. Petra, what's part B want me to find? You're right, say it nice and loud. So I'm going to write down I equals, I don't know. What did we just find in part A? What else did they tell me in the question that I could use if I knew the voltage that might help me find the current? They told me R? Are you serious, Mr. Dueck? This is Ohm's law? Yeah, this is Ohm's law. What was the resistance? 0.0. Oh, if I know V and if I know R. Now, I'm going to start, instead of using a V, I'm going to start using the EMF just to distinguish that this is an induced voltage and get you used to it. But this is V equals I times R. I guess I equals V, E over R. 0.045 divided by 0.025. I'm going to use the full value of 0.04512 divided by 0.025. Oh, almost 2 amps. 1.8 amps. That's actually not bad. Is that okay? A little clever, nice review. Ashley, what's part C want me to find? Magnetic force. And what did I find in part B? Is there an equation for magnetic force that maybe contains current in it? On a wire? Bill, you say? Our friend Bill? Oh, cool. Magnetic force is Bill. By the way, this is also a nice review for the last unit, which is why I almost always try and get this lesson in before the test anyways. Lots of right-hand rule practice. What was the magnetic field in Tesla's? 0.8? 0.08. 0.8 or 0.08? Current was 1.8 amps. I'll use the full value. Length was 12 centimeters, right? Yeah. Okay. .08 times that times 0.12. I get 1.73 times 10 to negative 2 newtons. Is that okay? What if I moved it faster? So what if little v got bigger? What would happen to my EMF? Bigger, smaller, or stay the same? Bigger. What would happen to my current if my EMF got bigger? Bigger, smaller, or stay the same? Bigger. What would happen to my force if my current got bigger? Bigger, smaller, or stay the same? Callum, the faster you try and crank that thing, the more you're gonna feel it pushing back against you. Hey, what if they're not moving? Oh, no current, no zero. So then Faraday and Henry said, well, what if instead of moving just a straight wire, what if we try moving a coil of wires? What if we move a loop? Do we still get an induced voltage? Well, Faraday said, it seems to me that I can think of this loop, I'll do it rectangularly instead of circularly, and I can really think of it as 4 wires. I can think of a little positive charge right there, a little positive charge right there, a little positive charge right there, a little positive charge right there. And I'm going to tackle each one separately. Let's start with the top chunk of wire. Now the velocity is to the right. So let's all of us in this top chunk of wire point our thumb to the right. Which way is the magnetic field? So I'm going to do that. Which way in that top chunk of wire, which way will that charge feel a force? This top chunk of wire feels a force down the page. Let's do the bottom chunk of wire. Moving to the right, magnetic field. Well, you know what? Here's the problem. Although they feel a force somewhat down the page, we're not talking about the force. We're interested in the voltage. Can you really separate charges here? Why not? Because the top section and the bottom section of wire are moving parallel to the velocity. This is the same situation, Jordan, as we had right here. Right here. Okay? So we're going to take our pencils. We're going to say, even though there's a force, we're going to scribble that out, scribble. Nothing. You know what? That top and bottom section don't do much. Yes, Neve, you can separate the charges a little bit, but they can't go anywhere. You okay with that? Let's look at the front section of wire. Here. Which way is the charge moving? To the right. Which way is the magnetic field? Out of the page. In the front section, which way will the charge feel a force? And it can move down because there's wire below it. So it's going to start to move that way. The current will start to go that way. Let's look at the back end, the back chunk of wire. Which way is the charge moving? To the right? You know what? It's going to feel a current, a force, that way. Do you see the problem we're going to run into here? I'm going to have current going this way, current going this way. Hey, if I have 1 amp moving to the right and 1 amp moving to the left, what do I really have? Nothing. Nothing. The induced voltages, the charges are going to get pushed against each other, and they're going to cancel each other out. Okay? I saw Nate's eyes light up when I said coil. He thought, oh, yeah, that might work. And Faraday drew this out. No. But he was one of the greatest experimentalists of all time. He's not done. We're not beaten. We can do better. Okay. Next page. So Faraday said this, if I supply motion and that induces a current, what if I supply current? Will that induce a motion? We talked about this. He was really interested in the idea of electric motor. What we're really talking about here, you may have heard the term, is a railgun. Have you heard the term railgun? A railgun is a gun that uses electricity to fire a projectile really, 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 really fast. So in this circuit, the wire strip is initially at rest, but we're going to supply a power supply to the circuit. We got a battery. See it? Right there. It says, for the circuit below, find the induced voltage. What's the direction of current in the circuit? What's the direction of the okay. First of all, part A says, find the induced voltage. Well, induced voltage is B LV. Why can I tell you right now that the answer is 0? Not moving. Okay? No induced voltage. We'll supply some voltage, but we're not getting voltage from motion. B says, what's the direction of the current in the circuit? Okay. This way. Right? This way. Right? This way. Right? That way. It's circular. You know what? Counter clockwise. Gonna make it clear? You sure? Hard joke. Claire needs your help. Okay. Manisha, what's C want me to find? What? Oh, okay, hang on. Now that I got this battery here, see it, what we've drawn? We have a current, see it? Which means because of the battery in this wire, charges are moving upwards. Let's all of us point our thumbs up. Which way is the magnetic field? Out of the page. Which way will this wire feel a force? To the right. It's going to start to accelerate. This is a railgun. By the way, instead of a wire, think a projectile made out of metal. Okay? This is a railgun. It's going to start to speed up. What happens to the strip? Starts to accelerate to the right. Kelly, you with me so far? Good right-hand rule application, okay? This was in the first Gulf War, for example. This is one of the concerns. They felt that Iraq and Saddam Hussein were trying to build a rail gun. So they were intercepting ships that were heading to Iraq, and the ships were saying, no, 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 these are big, long pipes for oil pipelines. Well, they're big, long pieces of metal. You can use them for other rail gun, okay? So there was some suspicion. Ah, now it gets cool. So Aaron, you agree with me that this metal bar, this piece of strip, the strip of wire, is going to start to accelerate to the right? What that means is this. Not only do I have charges moving up because of the current, I also have charges moving sideways because they're locked inside that bar. Point your right thumbs to the right because that's which way the strip is moving. Which way is the magnetic field? Out of the page. Which way will the charges locked inside that strip feel a force? The battery is exerting a force, a current pushing them this way, but as soon as they start to move, I'll change colors, they're going to start to feel a force that way. They're going to start to feel an oppositional voltage, an opposite voltage. It's going to actually behave like, hey, we did this before, two batteries facing each other, which we did do a couple of units ago. Okay? So, as it speeds up, what happens to the induced voltage? Well, since this is BLV, the induced voltage increases. Okay? However, the net voltage decreases. What happens to the current? Well, current is net voltage divided by resistance. Yeah, it's V total, but since this time I have the voltages in opposite directions, I'll call that the net voltage, the combined. So what happens to the current? Decreases. What happens to the magnetic force? Well, if magnetic force is Bill, if current gets smaller, what happens to the force on the wire? Smaller. So what happens to the speed? You with me? But Alex, as soon as it starts to slow down, as soon as that gets smaller, what happens to the induced voltage? gets smaller, which means your net voltage gets bigger, which means the current gets bigger, which means the force gets bigger, which means it starts, in fact, what's going to happen, it's going to take off really fast, but there's going to come an equilibrium point where it's no longer going to accelerate. It's going to start to slow down, but as soon as it starts to slow down, it's going to get a little nudge to speed up. It's going to slow down, get a little nudge. You're going to get a maximum speed. You're going to get a maximum speed. Where, and you know where that maximum speed is going to be? I can tell you where it's going to be. If this is a 6-volt battery, when the induced voltage equals 6 volts, because then your net voltage is what? 6 volts this way, 6 volts this way. What's your net voltage? 0. You're going to max out your speed. You're going to reach your equilibrium point when the induced voltage, which is in the opposite direction of your source voltage, when your induced current, which is in the opposite direction of your source current, exactly cancels out your source. Nice applications of right-hand rule. Kind of cool. To explain your answer using relevant principles of physics, we just did, I think. So, this setup has 2 applications. First one is nerdily cool. We could use this to launch vehicles from the International Space Station without needing rocket fuel. All you would need are large solar cells to make current for the circuit. We got those. And electromagnets, solenoids. Hey, those are easy to make. And you would use the metal ship itself as your conducting strip. So here is the... Okay. We want to launch this to the right. Would this work? Well, let's see. Here's our battery. Here's our battery sending current this way, sending current this way. So through the ship itself, the current is pointing down the page. Which way is this magnetic field? Look at the picture with the B. Which way do I have this magnetic field set up? Into the page. So current down the page, magnetic field into the page. Hey, which way will this ship feel a force? To the right. It'll launch. No need to fire a rocket close to the ISS. Good. Now, right? If you can't bend that way, rotate your paper 90 degrees. Right? The other place is electric motors, where a coil spins in a magnetic field. When a current runs through it, the coil experiences what we call motion voltage, often called back EMF. This is why the faster you rev up an electric motor, the cooler it runs. We're going to talk about that in great detail in lesson 5 or 6 of this unit. One of the last lessons we do. So, as the strip, example 12, continues to speed up, although at a lesser rate, acceleration gets smaller. The induced voltage will continue to go. What happens when the induced voltage equals the supply voltage? What happens when this equals A, the strip moves at a constant speed. B, the strip continues to speed up. C, the strip begins to slow down. Explain your answer. Well, if that what's my net voltage if my induced and my source are the same? So what's my current? So if there's no friction, it'll move at a constant speed. If there's friction, it'll start to slow down. But as soon as it starts to slow down, even a tiny bit, now you've got a tiny bit of extra source voltage, because now they don't quite balance. The EMF a little bit smaller than the source voltage. You'll have a tiny bit of current, tiny bit of force. Okay, it'll go at a constant speed, in theory. Okay. What speed? I wonder what that... Oh, let's find out. Example 13 says, find an expression for the maximum speed of this rail gun. Okay, What is the maximum speed? When the source voltage equals what? When the source voltage, the supply voltage, equals the EMF, the induced voltage. Okay? So you ready? Cliff, you good? Go ahead if you need to. So what's the maximum speed? So for maximum speed, here's our argument. I'm not going to call it part A. I'm going to say, well, first of all, maximum speed occurs when induced equals source. Okay? Let's go further than that. When BL little v equals big V. I guess when there's your maximum speed. Take your source voltage, divide it by the magnetic field and the length of wire.
So is that voltage or?
I don't know which one has wings, which one doesn't have wings. Yeah. I snuck that in earlier this year, right? I also knew this was coming down the pipe. Okay. There's your maximum speed. Oh, and for what it's worth, big V also equals I times R, where I is force divided by, is that right? F equals Bill? Yeah. In other words, I can mix and match a lot of stuff here. Railguns. Kind of cool. You want to get it to go faster? Hook it up to a bigger battery. Hey, you want to get it to go really fast? If you can get a battery, a source voltage of like a couple 100,000 volts, that's going to go. I got 9 minutes after 1. I'm not quite, this is the last one though, right? It is. So I'm not quite going to finish. I'm going to start next class with example 14. But questions you can do right now, certainly. Number 1. Number 2. Hey, looking at number 2, which length am I going to use, the 60 or the 14? The 14, the one that's perpendicular to the velocity, right? 3 is fair game. You can try 4. That may be number 14 that I'm going to get to next class. 6 is cool, but 7 is good. Comic. Did I include that in your notes? I think I did. Yeah? Okay. There you go. So I'm going to assign a couple of more next class, but for now, you can try those. They're nice reviews of, hey, right-hand rule stuff.